Hey class, this is Mr. Roberts, and I wanted to join you because I selected a problem type in our practice today that will allow us to kind of more deeply think about what's happening with exponents. What are they, and how we can use them to simplify some expressions. So I want to review a couple things with you. The first thing is two of our laws of exponents. We know and we've seen that if I have a power like x to the m, this is a power that's raised to a higher power, right? This is equivalent to x to the m times n. And if we go back to, how we think about this, like if I have this would represent three factors of x, right? This is x times x times x. And if I say, well, I want to have two of those, right? What I now have is x to the third times another x to the third. So I have a total of six factors of x, right? I can write this as x to the 3 times 2, which is just x to the 6th power. Now, what we often don't think of is the fact that this actually goes both directions. There's no reason why I can't start with some expression here and then use this relationship to go back to this way. So, for example, let's say that I have x to the, I jotted down something. Yeah, let's say that I've got x and it's being raised to the 3w power. Oh, okay. Something to the 3w power. Well, this is a product, right? So I know that I can break this down, right? I can rewrite this as x to the third, and then that gets raised to the w power, right? So I just want you to be aware that not only can I go from this left to the right, but I can also start here and use this relationship to go this direction also. The same thing is true for this law of exponent, right? If I have x to the m times x to the n, that's the same as x to the m plus n power. And again, if I think about this, I've got factors of x. I can have 5 factors of x, x times x times x times x times x. And I can multiply it by an additional 3 factors of x. So now I've got x to the 5th, 5 factors of x, times 3 more factors of x. That becomes 8 factors of x, x to the 8th. Same idea, we can have this and go backwards. So for example, if I have, let's say that I've got x to the, I'll use w again, x to the w plus 6 factors of x. I can use this relationship and write this backwards. So this is the same as x till the w, right, times x to the 6. So I know I have at least 6 factors of x, and depending on what w is, I could have more, and technically if w is negative, I could have less. Again, the idea that I want you to think about is that this can go backwards. Now, here's the problem type that you're going to look at today that's going to make us scratch our heads a little bit. And it goes like this. So I have some function f of x equals, and you can see my 0th term is 2,000, and I'm multiplying by 1.3 a bunch of times. How many times? Well, it depends on what value of x is. So in order to do this, so if x is 5, right, it's actually 17 factors of this thing. So my goal is to rewrite this so that I don't have to keep doing, evaluating this expression so that I can then evaluate this. I want to transform it into something that looks like this, a function with a new starting value, a, and perhaps a different base. But instead of having this expression, I just want it to be the single exponent of x that's up on here. And it's not, it seems a little intimidating, but it's not, I don't think it's as bad as it once we're done, I think you'll agree it's not as bad as it might look. So what I'm going to do is I'm going to begin by breaking this up. You can see I've got the 3x plus 2. And I'm going to break this up using this second idea that we have here, right? I can take this sum and I can break it up into two things as long as the bases are the same. So I'm going to go ahead and rewrite just this 1/3 part, or 1.3 part. I'm going to write this as 1.3 to the 3x power times 1.3 to the second power. And I still have this number 2,000. I'll go ahead and rewrite it. And this is still what f of x is. So I've made a pretty significant change in that this is actually a number I can calculate, right? This, I don't know, it depends on what x is, but it turns out this was just this lurking two factors of 1.3. So I'm going to grab my calculator because I'm not great with arithmetic. And I want to take 1.3 and square it. So 1.3 times 1.3. There it is. And when I do that, I get that this is the same as 1.69. So I have 1, 2, 3 things that are being multiplied. I'm just going to go ahead and do the commutative property and multiply the 2,000 times the 1.69. And when I multiply these together, times 2,000, I get 3,380. So this is now equals 3,380, and then times 1.3 to the 3x power. So that was kind of a significant change because now I don't have this plus 2, right? That plus 2 is gone because it ended up being two factors of 1.3 that I've incorporated in with the 2,000. Now I'm going to use the first idea from the thing we talked about, which is this one. I have here 1.3 to the power of 3 times x, 1.3 to the power of 3 times x. And I know that I can take that 1.3 to the power of 3x, and I can rewrite this as 1.3 to the third, and then that gets raised to the x. 1.3 to the third to the x power, and then this is still 3,380. Well, this 1.3 to the third power is just a number, so I'm going to go ahead and evaluate that 1.3 to the third power, and I get that that's the following. I get that that's 2.197, and at 2.197, that's what this is to the x power, and this is 3,380. Okay, so my claim is because of these two laws of exponents, power to a power and a power times a power, that this version of f of x is equivalent to this version of f of x. And I want us to consider some evidence for that. So let's graph the original function in Desmos. When I take a look at it, you can see that I do have the 2,000 times 1.3 to the power of 3x plus 2. And I'm going to go ahead and type in our simplified version here, which was y is equal to 3,380. And then it was times, we had 2.197 to the power of x. And when I do that, you can see that I have some, let me put on the high contrast, I get some pretty compelling evidence that these two things are equal to each other, right? Because you can see if I turn this off, this is the original and the green is the new one. And they seem like they have all the same XY pairs in common, right? If an XY is a solution for one, it appears to be a solution on the other curve as well. But moreover, the reason why that's true is because of our friends right here. And the reason why this is true is because these two laws of exponents are true. So I hope you found this helpful. I'll talk to you later in class. Goodbye.